Greetings from France, and today I'm going to talk to you about some of the initial research results of collaboration with a colleague of mine, Joanne Cohen, who I think is also watching this presentation right now. And as said before, my name is Laercio. I'm a research scientist at the National Center for Scientific Research in France and a member of the LRI lab. And I'll follow with this presentation. I'm going to follow a very traditional structure for the presentation, and we'll jump directly into our motivation. And well, the motivation here, I may be preaching to the choir, but the idea is that we have our applications that grow in scale, and they have bigger problems, more complex problems, they have more parallelism, and we have our platforms that are also increasing in size, more cores, maybe more nodes. And with all this increase in parallelism, what we have too is more potential for issues with loading balance. So this is actually really related to maybe the presentations in load balancing later today, but I'm in another continent, so the timing could be bad for me. And the things with loading balance here is they may come from the dynamic behavior of the application, they may come from performance variation of resources, or recovery from failures, or other issues that may appear during the execution. The standard way that we can try to fix loading balance during execution is by doing dynamic load balancing. It works well for several cases, several scenarios. Nevertheless, as we're worrying about scalability here, an issue may come with the overhead of centralizing information for the load balancing decisions, and also the sequential decisions that can be done in an algorithm like that. I mean, hierarchical load balancers can try to help on that, but we're thinking about another way to try to solve this issue is related to distributed load balancing. And this helps us avoid centralized information, and we see distributed load balancing in some ways, for instance, in work stealing in some runtime systems. We've seen papers in the past years related to also work stealing or dynamic load balancers that are distributed. Our work with Vinicius Freitas and other collaborators and colleagues were related to trying to batch tasks together to try to make decisions more quickly and also to keep some locality. Last year, we saw a presentation related to distributed load balancing in this same Charm++ workshop. And there are some other works, let's say, that try to bring something like distributed load balancing to our current and real runtime systems. But as I see it, we don't see many algorithms out there used in practice. And we want to have a vast trove of distributed load balancing algorithms, be it for comparison, be it to try to find something and improve and evolve. So one way that we were thinking about is what about looking for distributed algorithms from like problems that are related to scheduling and load balancing, but are not exactly the same that we see in our systems. For instance, balls and turbines problems, or problems related to game theory, or problems related to consensus. And instead of trying to reinvent the wheel, to see what can be brought from these algorithms and apply them to our high-performance computing scenario. And the main issue here is that when people are working on these distributed algorithms, they're focusing on very abstract models, which are far from the reality that we see for our applications. And they try to use little to no information because that helps them see the bounds or the conversions, improve the conversions of different algorithms in situations that you may not even know how many resources or how many tasks you have around. So these are very abstract, not easy to implement and apply directly. So what we've been trying to do together is trying to bridge this gap between theory and practice on distributed load balancing algorithms. And we've been doing some things together. The one that I'm going to talk to you today in our approach is related to finding ways to adapt and to improve distributed scheduling algorithms that are out there to be used in our real systems. So moving to the approach, what I'm going to show to you today is related to one specific work where we're taking an algorithm from the literature and trying to expand on it. So this algorithm was proposed by Petra Berenbrick and colleagues in the paper called Distributed Selfish Load Balancing. We're going to call this algorithm selfish. And the algorithm, it follows a structure of routes. So we have this M unitary tasks, and we have this N identical resources, and the tasks are spread throughout the resources. What we're going to do in a round is that we're going to take all tasks in parallel, and for each task, we're going to check the load of its current resource and the load of another resource at random. And if this new resource has a load that is lower than our current resource, we're going to try to migrate this task with a certain probability, and the probability is related to the ratio between the loads of these two resources. So the larger the gap in load, the larger the probability that the task is going to migrate. And the algorithm is really interesting because, I mean, it's very simple. It's not using much information at all. And it's supposed to find an epsilon Nash equilibrium in log the number of tasks, which is very, very fast. And it's also supposed to find a perfect balance with high probability in log m plus n to the power of 4. We look at this and we think, well, we can do several things to this algorithm to try to adapt it to our real systems. But as we were thinking about it, we chose to focus on the simplest thing that we could use and do, and to do a first step adapting this algorithm. So the first thing that we do is that we're going to add information related to the average resource load. In our case, it's the number of tasks divided by the number of resources because the tasks are unitary. We use this information to organize the resources in three classic kinds. We have the underloaded resources that are under the average load. We have the average loaded resources that are between the average load and the average load plus an epsilon, for instance, let's say 5%. And we also have the overloaded resources that have a load that is above this limit. And using these three kinds of resources, we can change this algorithm to try to define which resources can try to send tasks, which are our sources, and which resources can try to receive tasks, which are our destinations. And having these three kinds, we can build a simple 3x3 matrix where in each line we have a different rule for the sources, and each column we have a different rule for the destinations. So, for instance, the superior rule for sources mean that only overloaded resources can try to send tasks. The average is average loaded or overloaded, and the inferior is all resources can try to send tasks. On the destination part, the inferior means that only underloaded resources can receive tasks. The average means that average loaded or inferior or underloaded resources can receive tasks, and the superior means that all resources can receive tasks. So if we follow the rules that are for source and destination, inferior, superior, we have the original selfish algorithm, and we can also be the most restrictive and far from this algorithm using the superior, inferior rules. So the changes to the algorithm in this case is that we're only going to consider tasks from an overloaded resource, and when we're going to do the comparison between the load of these two resources, we're also going to check if the destination resource is underloaded. And we're only going to do a migration with a certain probability if that's the case. So we have this 9 variations, I mean the 8 variations plus the original algorithm, and then we move to our experimental evaluation phase. And this evaluation is based on a simple simulator that I wrote using Python. I have to update the latest version of this unified scheduling simulator to have this distributed simulators integrated. And we were using simulation because we're trying to understand several of the details of these variations. And it's easier to run more tests because we can require a lot of resources like core hours to do experiments with distributed load balancing algorithms. Just to give you an example, earlier this year we submitted a paper. We were working with one benchmark and around 1,000 cores, and with the debugging, finding the good parameters for benchmarks, running the experiments and having a statistical significant results, we got over 40,000 car hours. So as we grow in scale, this can also grow very quickly. But here we're also focusing on having some easier debugging, and simulation is easier to reproduce and replicate the results because the simulator is deterministic. We're only changing the random number generator seeds to have different samples. We gather 3 metrics. The most important metric for us is the number of rounds for conversions because the algorithm follows rounds. And in this situation, the thing that we would like is to reduce the number of rounds for conversions when compared to the original algorithm, but it may not be the case, right? We're going to evaluate that. Other 2 metrics that are interesting are the number of task migrations, because this relates to how much data has to be moved, and number of load checks, because this relates to the communication between resources to gather information about the load of another resource. Before moving into more details about the experiments, I'll just have to put our hypothesis here that we're trying to test. I'm not going to run through all of the hypotheses right now, and in this presentation we're only going to cover 3 of them, but they're registered here, and later if you're watching this on YouTube, you can pause the video here and read all the hypotheses that we have. I'll read some of them later in this presentation. So more details about the simulation. So all tasks are making decisions based on the information that we have available at the start of the round. So at the start of the round, we have the load of a resource, and we have a fixed load for the other resources. All tasks are going to use this same information, and the information is going to be updated for the next round in the simulation. So we don't have to worry about ordering messages and the asynchrony in the simulation. We can just do a sequential simulation that's going to provide always the same results. The simulation stopped if a scheduling algorithm is not able to achieve conversions in 1,000 rounds to limit the time that these simulations can take. And we define conversions here is the situation where no resource has a load that is 5% over the average resource load. So if the average is 100, if everyone has 105 or lower, it's okay. If we have any resource has more, we go for another round. Okay, so about the simulation that I'm going to discuss, we have several numbers of resources. They are not very large here because we're trying to understand the algorithms in this initial research, and then we can expand later. We're changing the average number of tasks per resource between 50 and 100. All tasks are unitary in this experiment, and we have 31 different initial task distributions. So we have one distribution where all tasks start in the same resource, and then we have 10 that follow kind of a normal, kind of exponential, and the CDF of an exponential distribution. Combining all of these scenarios with the 9 schedulers and 10 samples, which means 10 different random number generator SIDs for this each scheduler in each scenario, we have over 20,000 samples that were gathered here. Just to show you what I mean by the distributions. So here we have three figures with the examples of initial load distributions for 100 resources and a total of 10,000 tasks. So in the left, we can see it follows a normal distribution. It's important to say that in this histogram, each bar is actually the load that we have in 5 resources together. And in the middle, we have our exponential, and in the right, we have the CDF of the exponential, which is kind of like a logarithm curve here. So we see a lot of loading balance in the normal and exponential distribution, and the CDF of the exponential, we see that they're close to the average, which would be around 500 here because we have buckets of 5 resources, but there's also some resources that are severely underloaded. Okay. Having that, we move to our first hypothesis, that when compared to the original selfish algorithm, the addition of the average resource load, it should decrease the number of rounds necessary for convergence. What we have in this table is the mean, the average number of rounds for convergence for all the experiments with each of the 9 variations of the scheduling algorithms. So different numbers of resources, tasks, and distributions. They're all bunched up here in one single number, okay? And in the last row, last column, we see the value of 41 for the original selfish algorithm. And we see that the other values are smaller than that, which would indicate that on average, we're taking less rounds to converge. When we look at the details, we also discovered that there were some cases where the algorithms did not converge in 1,000 rounds, especially for the original selfish algorithm and for one of the other variations. We discount them when computing the average. We see that the average decreased, but not much, and we still see a difference. But the mean of a bunch of values doesn't mean much in the general sense for us. But for instance, if we look for the median number of rounds for convergence, we see that the median number tells us a slightly different story, because if we look at the first column where the destinations are set only to be the underloaded resources, the median number is actually higher than the number that we have for the original selfish algorithm. So in a sense, we see that there's more to be investigated here. We cannot just base everything on mean here. So another way to represent these results is by comparing the variations in the original selfish algorithm in this figure. So what we have here is each line is one of the variations, and the value that we have is related to the value that the average number of rounds that we have for a variation for a given scenario, number of tasks, resources, and original task distribution. And we subtract from this the average number of rounds that we have for selfish. We sort these values for each of the algorithms, and then we plot them here. What we see is that the original selfish algorithm, it's performing very poorly for around 25 cases. Then at this scale, they seem to be kind of similar. And then there are some situations near to the x-axis, near to 250, where other algorithms are performing very poorly. If we zoom in here, what we see is that after those initial cases where the original algorithm performs very poorly, we see this, for instance, this red, blue, and pink lines that are above the others that are performing worse than the original algorithm. And these 3 lines represent variations on the algorithm where only the underloaded resources can be used as destinations. Those are the first column that we had on our table. So this provides us some extra lessons that maybe using only underloaded destinations for this algorithm can be a bad idea. But we also see that there are 2 lines that are the lower ones the purple and brown lines, which are selfish average, average, and selfish average superior, which say to us that using overloaded and average loaded resources as sources can be a good idea. It's not always a good idea. There's a situation where it's not performing that well, but it's just some extra lessons that we took from these initial results. When we go to another hypothesis, the hypothesis 6, where we're thinking about the original task distribution, where we're thinking that the original task distribution, the original mapping before scheduling, it can affect the number of rounds that the algorithm is going to take to converge. So we would expect to see with different task distributions, we would see different numbers of rounds for the different algorithms. What we have here are 3 figures, each figure for one variation of the selfish algorithm. So we have on the left the original, in the middle the average, and on the right the most restrictive variation of the algorithm. And in each figure we have on the y-axis the average number of rounds it takes to converge for that algorithm, and for each column, each bar is a different initial kind of distribution. For instance, exponential covers the 10 different exponential initial distributions for different numbers of resources and numbers of tasks. And we see some interesting results here. For instance, for the original algorithm, we see that the single, where all tasks start in the same resource, is actually converging faster on average than the other ones. And meanwhile, the most restrictive algorithm, the original single mapping, is actually providing very, very poor results. And while for average, there's not a large difference between these results. But again, these are averages. They hide a lot of information. If we change our view, instead of using the averages, we're plotting the results using box plots, we can see that for the original algorithm, usually they are very close to a small number of rounds. There are a lot of outliers that go up to 1,000 when the algorithm doesn't converge in time. For the most restrictive situation, we see that the initial task distribution of a single one is providing a large variation of bad results. Meanwhile, for average, we see that in the worst scenario, we were taking up to 20 rounds to converge, which is much, much faster than this other variations. And when we see all the different box plots for the different distributions, they are basically the same without considering the outliers. We have some statistical methods that we have used for the evaluation, but that I'm not going to cover them in this presentation. Finally, the last hypothesis is that the higher the number of resources in a scheduling scenario, the higher the number of rounds that we're going to take to balance the load. And this may be counterintuitive if we think about the complexity of the convergence for an epsilon Nash equilibrium that was only related to the number of tasks. But we would think that by having more resources, it may be harder to find a resource that will receive a task. And this is kind of what we're seeing here. So we have 3 figures for the 3 different algorithms that we had for the previous hypothesis. In this case, we have the average number of rounds in the y-axis, and each of the bars is a different number of resources. And as we see here, in general, as the number of resources grows, also grows the average number of rounds. But there's something hidden here, is that we're having 50 tasks per resource in these situations. So actually, when we're increasing the number of resources, we're also increasing the number of tasks in our system. But, well, we can see that if we compare for the same algorithm, the same number of tasks, for instance, in this case, 5,000 tasks that are in the left distributed over 100 resources, and on the right, distributed among 50 resources, is what we see is that there's still a jump in the average number of rounds that it takes to converge. So there's still a difference here, even when the number of tasks is equal. And what's interesting when we're also comparing these two figures is that we see that the more tasks per resource we have, the faster it is to converge. So it's easier to have a load of 105 tasks or lower with 100 tasks per resource on average, when compared to 50 tasks per resource, where the conversions would require at most 52 tasks. So a lot of having a lot of tasks in these situations is good for conversions. So to conclude this presentation, these were only some of our first steps trying to bridge this gap between theory and practice in distributed load balancing. The hypothesis that we had for these experiments, they seem to hold. But I mean, we're still planning to run on larger experiments with some other hypotheses that come after these first experiments. So we want to run larger scale, for instance, more resources, more tasks, or even less tasks to see how it affects the results. Run experiments with non-unitary tasks, which reflect what we see when we're running a real application in Char++, for instance. Try to add more information and techniques as we see the algorithm converging to a good solution for systems, and then try to implement it in something like Char++ and try to run it in a real HPC system. But first we have to filter the variations. If not, we're going to require all the resources available in the supercomputer to run our experiments. Just before finishing this presentation, I'd just like to have two final remarks. The first one is that I think as a community, we should really get some standard load balancing simulators. And I have some ideas of simulators that are not focused on load balancing, but can be used for that. Today, I learned also about the load balancing analysis framework from Dharma. And if you know of any load balancing simulators, I would love to know more about it. And this should make it easier for us to compare algorithms and results, and it should help us avoid counting on supercomputers all the time. And the second thing is that I think we really need some standard load balancing benchmarks with well-documented parameters. And these well-documented parameters are important because if we change, for instance, the scale we are running a benchmark, it may also change the loading balance that we see there. So having these well-documented parameters should help us be more productive when running these kinds of experiments. I see Task Bench doing some nice work in the right direction, but I don't think that's just a solution for us right now. They're not focused on load balancing. As far as I know, they don't even have persistence load imbalance right now in Task Bench. So I would like to thank you all for coming and seeing my presentation. And if you have any questions, I'll be happy to answer them now, or my email is available for your questions. Thank you.
Thanks for your talk, Laercio. Does anybody have any questions? I don't see any on the Google Doc, but if anyone has anything, feel free to ask just now. There was some discussion about complexity in the Zoom comments here, but it seems like that's been answered.
Oh, yes. It's the last option, log m plus n to the fourth power.
I think I would like to endorse your point about needing that simulator. I do think that we probably have done it a couple of times and dropped it a couple of times. So we need to bring it back. But the simplest point to make there is that we can do it because of virtualization, right? The same way we did in BigSim. You just pretend that you have 10,000 nodes by having 10,000 user level threads running as them, and doing the algorithms. As long as that is okay, then I think we can do that algorithm. And in fact, you can even do simulators even simpler than that for some of the algorithms that can just have a sequential program doing the behavior of the distributed algorithm.
Yes.
If you want to be kind of strict about the distributedness of it, you can do it with some user level threads or threaded methods, I think.
Yes, I agree. But we really need something more standard that, let's say, most of the people agree.
Yeah, on that front, Phil here, I'll be talking about the load balancing analysis framework in my talk later today. It doesn't handle task-to-task dependencies like Big Sim would, but it does capture some of the broad synchronization structure between sets of tasks, and maybe that can be a decent basis for this. And it means that you can just do the simulations entirely in a single sequential process using just statistics files.
Yep.
I'm not sure I'll be able to be around later today, but I'm sure to watch the video later if that's the case and contact you.
Yep, great, thank you.
And all the talks will be recorded and available later on, either on the YouTube channel and then later on edited versions somewhere.